Hey everyone! Today I'm going to be walking you through a pretty extensive engine problem from your textbook. This problem is going to touch upon PV diagrams and their analysis, as well as efficiency and a little bit about entropy as well. So if you're having any concerns drawing these PV diagrams or interpreting these PV diagrams, please keep watching because I'm going to address all these concerns. This problem states, in a heat engine, 3 moles of a monatomic ideal gas, initially at 4 atm of pressure, undergoes an isothermal expansion, increasing its volume by a factor of 9.5 at constant temperature of 650 Kelvin. The gas is then compressed at a constant pressure to its original volume. Finally, the pressure is increased at constant volume back to the original pressure. So for part A, we're asked to draw a PV diagram to illustrate the cycle for this engine. And we're also asked to label these axes. The problem tells us the amount of moles. It also gives us the initial pressure and the temperature. Given this information, we can use the equation PV equals nRT to figure out what our initial volume is equal to. Keep in mind, because we're given the pressure in atm, we must convert this into pascals. There is 101,325 pascals in 1 atm. Solving this equation, the initial volume turns out to be 0.04 meters cubed. The problem states that the next step is isothermal, and the volume expands by a factor of 9.5. Therefore, we know that the final volume of the gas after the second step is going to be 0.38 meters cubed. And since we are told that this is isothermal, we can set up a relationship between pressure and volume. P1V1 should equal P2V2. Plugging in our initial pressure and our initial volume, we can solve for our final pressure after plugging in the new volume that we just found. And so after this isothermal step, we get that the new pressure is going to equal to 0.421 atm. Knowing this information, I want you guys to pause the video here so that you guys can have a chance to draw your own PV diagram. Okay, so our y-axis is going to be pressure and our x-axis is going to be the volume. Let's also mark our 2 points of pressure that we know. So there is one at 4 atm and one at 0.421 atm. Let's do the same for volume. So our initial volume is going to be 0.04 and it's going to go to 0.38 in the second step. The problem states that our initial pressure is equal to 4 atm. And using PV equals nRT, we found that our initial volume was at 0.04 meters cubed. The problem then claims that the gas expands up to 0.38 meters cubed. And using PV equals nRT, once again, we found that our new pressure is at 0.421 atm. So now let's plot our second point right here. We are then told that the gas is compressed at a constant pressure to its original volume. The original volume is at 0.04 meters cubed, and the pressure is still 0.421 atm. And so now we have our third point. Finally, in our last step, the problem states that the pressure is increased at constant volume back to its original pressure. So now the volume is still at 0.04 meters cubed, but now the pressure is going to increase up to the original pressure of 4 atm. We are back to our first point, exactly where we started. Now let's draw in our direction line showing exactly how this cycle flows. So it goes from expansion to compression to an increase of pressure. Let's also label our points and our steps so that we can stay organized for our future problems. So our first step is going to be the expansion of gas step. Our second step is going to be the compression step. And our third step is going to be the increase in pressure step. Our first task is complete. This is our PV diagram. Now let's move on to part B and C. Calculate the work done by the engine during each step and the net work done per cycle. Find the internal energy change in the heat flow into or out of the gas during each step. So essentially we're finding delta U, W, and Q for each step. Okay, step 1. This is going to be our isothermal step, where we have constant temperature. And this is when we go from point A to point B on our PV diagram. What is unique about isothermal systems is that because there is constant temperature, the internal energy change is actually equal to 0. The internal energy change is equal to the heat flown in and out of the system plus the work done on the system. Since delta U is equal to 0, we can rearrange this equation and we get that the heat is actually going to equal to the negative work done on the system. As shown on your formula sheet, the work done on an engine or on a system for an isothermal system is defined by nRT multiplied by natural log of volume initial over volume final. We know that there are 3 moles of gas. We also know that the temperature is 650 Kelvin. We know that the gas expands in this step from 0.4 meters cubed to 0.38 meters cubed. Knowing this, we know that the work done on the system is negative 36.5 kilojoules. I just wanted to quickly reiterate that this equation we used here is used to define the work being done on a system. And so this is also to say that the work being done by the gas in the engine is positive 36.5 kilojoules. Once again, since this is an isothermal step, the work being done on the system is equal to the negative amount of heat. And so the negative Q in this case is going to equal positive 36.5 kilojoules. And since this is a positive number, we know that heat is flowing into the system. Let's do a recap. This is an isothermal step, meaning that the internal energy change is equal to 0 kilojoules. The work being done by the gas in the system is 36.5 kilojoules. And this also means that there's 36.5 kilojoules of heat flowing into the system. Time for step 2. In step 2 of the system, we are going from point B to C on our PV diagram. When we're going from point B to point C, we're keeping our pressure constant at 0.421 atm. However, we're compressing our gas from 0.38 to 0.4 meters cubed. Because we're not changing the pressure of the system, this is considered to be an isobaric step. Iso meaning the same and baric meaning pressure. Let's have another look on your formula sheet. There's another formula for work, which is equal to negative P delta V. In this case, this is still the work being done on an engine or on a system. Our pressure in this step is being kept constant at 0.421 atm, and we again have to convert this into pascals. The final volume of the gas after being compressed is 0.4 meters cubed, and our initial volume was 0.38 meters cubed. So the work being done on the system is positive 14.5 kilojoules. Now let's talk about the internal energy change. Another formula for the change in U is number of moles multiplied by the CV constant multiplied by the change in temperature. For monatomic gases, the CV constant is equal to 3/2 of the universal gas constant. Okay, so let's plug in our CV constant into the delta U equation, and what do we get? Well, this should look very familiar to you. Some people may start panicking because they don't know what the change in temperature is. Well, this nRT is equal to the same nRT in our PV equals nRT formula. And so this change in internal energy just equals 3/2 pressure times change in volume. This change in volume is going to be proportional to this change in temperature. Let's solve for our internal energy change, and let's plug in our numbers. Make sure again to change your atm into pascals. And so the internal energy change is negative 21.8 kilojoules. And so this means that the temperature has decreased in the system. Finally, let's solve for the heat flown into or out of the system. And since delta U is equal to Q plus W, let's plug in our delta U and let's plug in our work. And so Q equals negative 36.3 kilojoules. And since this is negative, heat is flowing out of the system. Okay, step 2 recap. The work being done on the system here is 14.5 kilojoules. The internal energy change is negative 21.8 kilojoules, and 36.3 kilojoules of heat is flowing out of the system. Finally, let's take a look at step 3. For step 3, we're going from point C to point A. Let's take a look at our PV diagram. From point C to point A, we are staying at the same volume of 0.4 meters cubed. For the pressure, however, we are increasing it from 0.421 to 4 atm. And because we are keeping the volume constant, this step is an isovolumetric, or also known as isochoric step. In isovolumetric steps, there's no work being done, so work equals 0 kilojoules. And this is because work equals negative P delta V, and since delta V is equal to 0, work is also equal to 0. And because there is no work being done, the internal energy change just equals the heat flowing in or out of the system. And again, delta U equals N 3/2 R delta T. And this can also be written as 3/2 times the volume times the change in pressure. And in this case, the change in pressure is proportional to the change in temperature. So the volume stays constant at 0.04 meters cubed, and the pressure changes from 0.421 atm to 4 atm. And again, let's remember that we have to keep this in pascals instead of atm. And so we find that the change in internal energy is 21.8 kilojoules. And since the change in internal energy equals the heat flow, then the heat flow is also equal to 21.8 kilojoules. And since this is positive, the heat is flowing into the system. Okay, our last recap. There is no work being done in this last step, but the change in internal energy is 21.8 kilojoules, and there is 21.8 kilojoules of heat flowing into the system. Let's look back at our question. The question asks for the net work done per cycle. The question also asks if the heat input per cycle is 58.3 kilojoules, what is the efficiency? In order to figure out the net work done by the engine each cycle, we have to figure out how much work is being done by the engine in each step. So in step 1, step 2, and step 3. Lucky for us, we have already calculated the work being done on the engine in each step. In step 1, there was negative 36.5 kilojoules of work being done on the engine. In step 2, there was 14.5 kilojoules of work being done on the engine. In step 3, there was no work being done. And to figure out what the work done by the engine was, we just multiply each of these work values by negative 1. So step 1, there was 36.5 kilojoules done by the engine. There was negative 14.5 kilojoules of work being done by the engine in step 2, and there was no work being done in step 3. This makes sense because in step 1, the gas was expanding, so the gas should be doing positive work. In step 2, the gas was being compressed, so the gas must have had work being done on it. Adding up all these values, we get that the net work is 22.0 kilojoules. The efficiency of a system is defined by the work output divided by the heat input. In this case, the net work output is 22.0 kilojoules, but there was 58.3 kilojoules of heat inputted. So the efficiency in this case is equal to 37.8%. In part E of this problem, we are asked to find the entropy change of the gas during the isothermal step. As mentioned before, the isothermal step is step 1. This is when the system goes from point A to point B. The change in entropy can be found by dividing the heat absorbed during the step by the temperature. We found that in step 1, there was 36.5 kilojoules of heat flowing into the system. Because this was an isothermal step, the temperature was kept at 650 Kelvin. We know that the entropy change was positive because the gas was expanding and becoming more and more disordered. We found that the change in entropy for step 1 was 56.2 joules per Kelvin. What is the entropy change of the gas for a complete cycle? Is it equal in magnitude to the entropy change of the environment per cycle? In order to answer this question, we must first ask ourselves, is entropy a state function or is it a path function? A state function is a property whose value does not depend on the path taken to reach a specific point. Path functions are the exact opposite. They do depend on the path taken to reach the point. In the case of entropy, we only care about the initial state and the final state. How ordered was the system before? How ordered was the system after? And thus entropy is a state function. We only care about the initial and the final states. And because our PV diagram shows that our engine is going in a cycle, we start from point A, we go to point B, then we go to point C, and then we go back to point A. Our initial and final states are the same. And so our change in entropy equals 0 joules per Kelvin. The second part asks, is this change in entropy equal in magnitude to the entropy change of the environment per cycle? The answer to this question is no. And why is that? Well, the reason is because this is an irreversible process. And according to the second law of thermodynamics, the total amount of disorder in the universe never decreases. Irreversible processes increase the disorder of the universe. And so the entropy change of the universe is going to be a value that is greater than 0. I know this video was lengthy and covered a lot of different topics. Please feel free to rewatch any part that you found confusing, and of course, please come to the Learning Center if you have additional questions or want to discuss the video further. Thanks for watching.